Okay, so today we're going to continue our talk about the Fourier series, but before we get going, are there any questions? Okay, so no questions just yet. So what I thought today we would do is a more formal look at calculating the Fourier series. All right. Which again, it's just a mathematical tool for breaking a signal up into sines and cosines. So let's take an example. Where we're just looking at this portion. The signal goes from 0 up to V peak in the period. All right, now again, I'm just concentrating on this portion, but remember this signals, right, are periodic. So let's find the DC component, which really that looks like a triangle. You get 1/2 base times the height. But let's just get our math warmed up. A0. We're going to take the average area, so that means we scale it by the period, right? Just a quick thing of what the period is. It's continuous time, so we integrate. We want to integrate over the whole period. Now, I'm just going to keep this as t. All right. We could change the slope, but really doing t is fine. All right, so we have t dt. Oh, derivative of it. All right, which is really t squared divided by 2 t naught, and we evaluate that at 0, and we evaluate that at t naught, and that equals t naught squared t naught minus 0, which gives us all right, which makes sense because 1/2 the base, all right, times the height is going to give us this. All right. So that's A naught, or the DC component, squared away. Now let's start calculating the ANs. Now sometimes it's, you might want to calculate A1, 2, 3, 4 to kind of see a pattern, but it's probably a good idea just to try to keep it general first. So 2 divided by T naught, integrating it up to T naught. And we have T cosine 2 pi to keep it generic with the ends. We put the n there. All right. Now, this can get a bit what we might call hairy, and that's going to give us n pi. Kind of went off the screen there, so I'm just going to put the evaluate over here. All right, I hope you forgive me. All right, so a lot of times things cancel out. So it's best just to notice how the ends and the t, or the t anyway, is inside a cosine or a sine. So what we can do is just evaluate that. Right. At 0 and T naught. And we just, what I like to do is draw a picture of the cosine function just to kind of remind me what I should be getting. So what we're going to have is cosine 2 pi n times the period divided by the period minus cosine 0, which is always 1. And then here we have cosine 2 pi n, right? And so if n is 1, we're at 2 pi. If n is at 2, we're at 4 pi, but that's just a whole period, right? So this will always be 1, okay? So this term, after all of that, all goes to 0. Right, because 1 minus 1 is 0. Let's look at the sign. Well, when we evaluate this at 0, it's always 0. And then when we evaluate this, it's 2 pi n, okay? Because the periods cancel out, and it's always 0. So in fact, the ANs all equal 0. Now, you could have done this by inspection by noticing that this is an odd function. All right, let's see what we're going to get. For Bn. Sorry, that's a sign. I see you. Yep. Yeah. Just so you know, that's not one that I have memorized, and I ended up I make integration tables with SIMP. But that's a good tip. Thanks. Okay, so if I look at the sign again, I'll just call that out, right? Either it's 0 because t is 0, or it's 0 because it's an integer of 2 pi. An integer times 2 pi is always going to be 0. So that's always 0. All right. Over here, we'll have so cosine of 0, it's -1, and cosine of here is 1, However, what I didn't put in is the t. So here, that t is 0, and it's 0. Here, that t is t naught. Okay. So we get t naught multiply that all through. So to summarize, let me just redraw it minus t naught m pi. Okay, so it has a DC component. It has no cosine components, and it has a sine component. All right, and so now x of t would be t naught divided by 2, and we would sum, we start at 1 up to infinity, and we can put the minus sign there. All right. And so just to do a few, right, just to see how it progresses. So we have the period divided by 2. Then we have minus t naught divided by pi sine 2 pi t divided by t naught. Minus. and so on and so on. And you just sum these up. All right. Now, this can actually be drawn on a spectrum. And this could be frequency, or it can be in radians. And it's not exactly a Bode plot because we're going to show 0. It's not a delta function. It's just saying at 0 hertz, this is T naught divided by 2. All right. And then here, this is at this frequency, we're minus T naught right, which is going to be smaller than the DC part because it's divided by pi, right? And then here would be and that's T naught divided by, a little over 6. And it gets smaller and smaller and smaller. So as this goes on, sometimes this is bigger than the others, but usually, and this can be bigger even than the DC, but then the other harmonics go to 0. Okay, and in this case, right, these are all, this happens to be A naught, B1, B2, B3. But since there's no AN term, right, it won't show up in this plot. And I'll give you another example of that later. But right now, just know that you can do this, and then you have, then you can calculate the phase as well from this. So that was that example. I thought we would do 50% duty cycle square wave next, because that features so heavily in our projects. Are there any questions so far? All right, moving on. All right, so let's say this is a signal coming out of a microcontroller. And it's just going on and off, on and off, on and off. forever because it's a Fourier analysis, and it's on 50% of the time, right? And the V peak, right, you could have a 5-volt microcontroller, you can give 3.3, and you can have 2.5 volts. These are your various choices, all right? So we'll call that VP, and we'll call this point T naught divided by 0. And so right now I'm just going to call XT all right, that's what XT is. So let's find A naught, the DC offset. Now, this function, right, it's discontinuous. It has a value and then it doesn't have a value. And so really you need to break it up into pieces. And in SIMPy, you can actually use a function called piecewise to put things together. And it actually comes quite in handy in using it to try to figure things out. All right. So the first half, right, is just a constant in that region, Vp dt, right? All right, and so we break it up. And so often what can happen is you might forget where's that 2 coming from. And it's really because we're just only integrating up to here. The rest is 0. So we just ignore it. Which makes sense, right? It's on for half the time. If it were on for the whole time, the average would be VP. If it was on for a quarter time, it'd be VP divided by a quarter, and so on and so on. And so in fact, in a pulse width modulated signal, it's in fact the DC that we want. The other parts, to turn it into a digital to analog converter, we actually want to filter out. All right. So let's do AN. So when we integrate that, we get at which point you might start to notice a pattern. Right? If I substitute 0 into sine, it's going to give me 0. Right? And sine 2 pi n, right, is 2 pi n. That's always going to give a 0. So in fact, all the ans equal 0. Okay. So now let's just evaluate what's going on with the cosine. All right. So we have cosine 2 pi n t naught divided by 2 t naught twos cancel, and we have cosine n pi, right? And if n is even, right, that is going to be plus 1. If n is odd, that's going to be minus 1. So if we come back, and when cosine is 0, that's 1. So if it's even, right, we get plus 1 minus 1 goes to 0. If it's odd, we get minus 1 minus 1 goes to minus 2, and we get 2 VP. And pi. So let's summarize. All right. Oh, question? Okay. So again, now we're going to get xt equals to VP divided by 2, right? N equals 1, that is odd. So we're going to get plus 2VP divided by pi sine. All right. Then the next n, so this is n equals 2. B naught is 0. It doesn't exist. Or B2 is 0. So 0 times sine, we're just not going to write it. Right? N equals 3 is all right. N equals 4. B4 is 0. And I'm just going to write the another term here for n equals 5. All right, and so on and so on. So I'd like to go back to our representation of drawing the spectrum. Okay. So if t naught equaled 1 millisecond and we wanted the frequency, right, just so we know that that'd be 0, 1 kilohertz, 2 is missing, 3 kilohertz, 4 is missing, 5 kilohertz. All right, DC is DC. And so we have A naught is VP divided by 2. All right. Now, for the next harmonic, we have 2 VP divided by pi, which is kind of like 2/3, right? Which is just a little bit bigger. Yep. So that's a great question. If you apply a low pass filter to that signal, and let's say a perfect brick wall filter, right? You would just get the VP divided by 2. Just that's how I was going to finish it up. I'll draw it on the picture once I'm. Then the next. So that's like 2/9, right? So it's smaller. And then we have here. And you can see it just gets smaller and smaller and smaller. Now, so this is our fundamental frequency, and then these are all the harmonics. But notice that at 50% duty cycle, the sine wave that's part of the original signal actually has a larger amplitude than what we want. Now, what did I mean by a low pass filter, a brick wall? Is that if we go look at our Bode plots, right, for a low pass, right, it passes, and then it slowly, it attenuates more and more and more as each frequency goes, but some of the frequency signals do get by, right? But a brick wall would be like this. And this would be 0, which of course you can't do on a Bode plot, but so it passes exactly what you want and none of what you want. So a perfect filter, a brick wall filter, well, I would just draw kind of a rectangle around that, and that would give me my DC. Now, sure, and what I'm going to do is just kind of redraw this. Well, no, that'll take too long. Sorry. So if I had now again, this is a linear scale, all right? And so this is log log. In a linear scale, you're actually kind of getting this S kind of thing. And so to draw the filter, I'd kind of, a real filter, I'd kind of get this. So that means I could pass up to here but I'm still getting some of that signal. Now, how much? Well, whatever the magnitude of the transfer function is, times whatever the magnitude of that signal is what you would be getting. All right.
Professor?
Yep. Sorry, I was when my phone rings, I try to look at it just to make sure somebody's emailing. But what's your question?
Yeah. Is it possible to express this function in summation notation?
Oh, you were cutting out a bit there. Could you ask that again?
Yeah. Is it possible to express this function in summation notation?
What kind of notation?
The summation instead of like because I noticed you just had this like the n equals
Oh,
1.
right. Well, I was trying to draw it out. Let's see how that fits the way I want it to fit. All right, let's see. So if I were to do this in summation notation, right, I have VP divided by 2 plus, because they're all positive, n equals 1, 3, 5, up to infinity. Then here we had 2 VP n pi. Since it's the b coefficients, it's all signs. 2 pi n t divided by t naught. Now there is a kind of a way you can get it to be n equals to, you can modify n so that you always get an odd number, but I'm not going to do that today. So did that answer your question?
Yeah, thank you.
Okay. So yeah. So yeah, that's a really good question. So if I have this square wave, right, it's made up of, we can break it up into this infinite sum, right? And if we recall that low pass filters, right, all right, so now I'm somewhat mixing, but if I take this rectangular waveform and put it into a low pass filter, right, depending on the frequency, right, it rounds it out. Now, I think to answer your question, it'll be easier to just show what's going on. And it's also good to show you because you can get an idea of what the difference is between Laplace and Fourier. So let's just run this for a bit. All right, and you can see that it's going up and coming down, right? But what you might not be able to see very easily is that it's going down to about 50 millivolts, and it's going up to almost 1, right? That's because I'm not letting it stay on actually long enough to fully go on, right? So if I just change this to, or if I just double it, right? You see that it fully rises, it fully comes down. And what happens here is happening down here. There's no change to it. But if I start to increase the frequency, all right, I'm going to turn off. So you can see the frequency is increased, so I'm going to turn it off. So I start at 0, and then notice it goes up to like 800. Then it, so yeah, it's speaking about 800, then it's a little above 160. And notice how it rises. You can see how it's almost settled to where it's going to go here, because you can see the peaks are all hitting that. But when I put it here, you can see that it takes time to get where it's going. And this initial setup is the Fourier, the Laplace can tell you, because it's got 0 initial conditions, right? But out here, where it's like steady, it's always going to it's rising up to the same level, going down to the same level. It's kind of reached a steady state, and that's like the Fourier analysis. Now, if I were to, and actually, I want it slower. All right. So, so now I just changed the time constant because it wasn't really showing me what I wanted, right? You can see that it goes up and it comes down, but then it goes up a little higher and comes down a little higher, and then eventually it seems to settle, all right? And interestingly enough, the time it takes to settle, because this is a first order circuit, is 5 tau, right? But after a while, those initial conditions, are averaged out. And if I just zoom in here, where it's the same no matter what, well, now we are in Fourier domain analysis, okay, where this is you're seeing kind of that infinite sum, because it's the whole idea. This is always periodic. It's always doing that. It's always been doing it, and will continue to always have done it, right? And if I change this frequency to even higher, All right. So that's how fast it's going off and on, right? You can see that it's headed. Look at where it's headed. Half a volt. And there's still some ripple, right? If I could completely get rid of the higher harmonics, this ripple would completely go away. The only thing I can do is just say, well, let me make it an even higher frequency. And now at this scale, you see it's a little blurred. There's the ripple still there, small, but still present. And if you want to see what's going on, there's our so there's our low pass filter, right? And that first harmonic, right? Where would I want that first harmonic to be? Do I want a 10 hertz pulse width modulated signal? 100 hertz pulse width modulated signal? Let's do 10 kilohertz, right? And so that's so the gain at that point is minus 100 dB. So that's that right at that point, right? That's the 2 times V peak divided by pi, right? And then at 30 kilohertz, that would be the next one in the sequence, all right? So all right, I see your question and I'm thinking about it. Okay. No. The question is yeah, what the problem would be is that if I had a series resistance here, right? And so this is not a realistic at all, right? I'm just making up these for an example right now. But any series resistance, yeah, it would form a voltage division and it wouldn't work. But no, this is just a low pass filter. And the reason why it's headed towards, so the DC part, right, is VP divided by 2. So in this case, V peak is 1, right? So it's going to go to V peak divided by 2. But now what I want to do is, what if that was at the 10 kilohertz that I originally, right? The gain should have been minus 100 dB, right? So that's 100 kilohertz. We don't really have to. We don't have to simulate for as long. Now it's taking longer to simulate because I'm simulating for 2 seconds and it's changing every 50 microseconds. All right. And I didn't give it enough time. All right. And while it's doing that, I'm going to calculate something. Okay. So you can see that it's going to V peak divided by half. That's the average. That's what we're trying to get rid of all those other components, and that's why we're headed to that. Now let me zoom in. I have to. All right. So the input, the change was 0 to 1, so that's 1 volt. At 10 kilohertz, we were supposed to have minus 100 dB of gain. So that means we should have a 10 microvolt signal coming out. And if I look at the difference, okay, instead of 10 microvolts, I'm getting 15. The reason why it's not exactly 10 is that kind of analysis only works for pure sine waves. The thing is this sine wave has the other harmonic. It's got the 10 kilohertz, the 30, the 50, and even though they get smaller and smaller, it's making that peak to peak just a little bit larger. All right. If I actually simulated a sine wave, right? Well, you'd see that I should get pretty close. Oh, now, of course, the reason why it's going towards an average of 0 is the sine wave is the average of 0. I would need to add 0.5, but this is good enough to just see what the Yeah, that's going. That's about right. Okay, getting about 10 microvolt peak to peak. All right. So that's the difference between the sine and the square. Now that was a pretty deep question, but that's really is where it's all headed, right? Um, so I'm trying to get back to my smooth draw. Okay. Oh, that was cool. All right. Well, that is the thing is I mean, that was a great question because really we spend a lot of time in this course talking about filters, right? But then that's like that's actually Fourier analysis because we set S equal to J omega and everything has to be periodic, and that means everything has to be a sine or a cosine, right? Um, and then when you have the Fourier spectrum, right, it ties it all into place, right? And then you would have to choose. Now I have other questions, right? And um, so yeah, if I want a pulse width modulated signal, actually I'm gonna redraw that. So let's say I have a spectrum, okay? Let's call that 0, 1K, 3 kilohertz, 5, and 7. And you say, hey, I want to make a PWM filter, right? Which, okay? So I have a PWM filter. Which part of the spectrum do I want? Well, I want and I'm going to put in quotes, DC, because in fact, you can change this over time. Um, meaning you can be at 50% and then you can be at a quarter, right? And then as time goes on, you can be at 3/4, right? And so you are changing this. This is actually, you're encoding your music or your motor. It's just, it's a lot less than this first harmonic. But what part do I want? I want this part. What kind of filter? Right? Low pass. Now, when you're doing this on homework and assignments, you can just draw it like that, or you could do the brick wall, even though it's not physically realizable, right? Another question, you know, I did the FFT of a signal. And it turns out there's a kilohertz noise I don't want. I want to get rid of it. All right. So what do I want to get rid of? Well, I want to get rid of this one. How do I get rid of it? A notch filter, right? Let's say I want let's say, for instance, that you're a student at San Jose State and it gets shut down with a COVID because of the COVID virus, and you don't have a function generator, and you need, just to make something up. Yeah, just totally random, right? And you need a 3 kilohertz sine wave, right? To really, okay. I need this, right? Because I'm doing some kind of test in which I need a 3 kilohertz sine wave. All right, well, what do I want? Well, this is what I want. How do I get it? Bandpass, right? And so, this is T naught, right? And if I want different, let's say I want different other things than 3K, right? What I can do is change the frequency of this, right? Although it might be better to actually take the 1K, take the first harmonic, adjust T1 to where the first harmonic is giving you 3K, all right? Now, what if you want to, I see you. Okay. Just let me answer that question in a second. So let's say I wanted to block, I need a different color. Block DC, right? So I'm going from here, but what I really want is this, right? Well, how am I going to do that? Okay. Now it doesn't have, I'm just saying, you see how this is a high pass function. Now, yeah, if I recall, so I'm going to go back to your question about what you would do, right? I need a band pass here, and if I recall, that was 2 VP, 3 pi, right? And now the thing is what I didn't really say is I didn't have any gain there, right? But let's say I wanted a gain of 0, right? I would say 0 dB. I would set my op amp gain to 3 pi, and the VPs would cancel out, right? And I would, let's see, bandpass. That would give me my bandpass, right? then I could put that into an op amp. And 1 plus R2 over R1. Three pi divided by 2. The VPs cancel out because that, if the V in is 1, then V out is going to be scaled. It's going to be scaled no matter what, right? And then that would raise the level. Almost sounds like a homework problem, but I don't mind. Okay. I guess that's it for today. Please don't hesitate to email me if you have any questions. But if you have a question right before we leave, I didn't see the chat. Anyway, that's really great. Okay, so have a good weekend, and it's coming. It's spring break next week. Now, please don't hesitate to email me any questions, but there won't be any class because, in fact, we didn't meet any classes, and I have to kind of practice and sort out doing online testing. Okay. All right. That's it. Have a good evening.